Okay, we talked a little bit about resistance, resistor, resistivity. Okay, now let's get into that a little more in detail. Okay, resistance of a piece of material, okay, is equal to the resistivity of the material in ohms per meter times the length divided by the cross-sectional area. Okay, recall the water pipe analogy we talked about. Okay, where you got the length of the water pipe and you got the cross-sectional area of the water pipe. They determine the pipe resistance, basically. You know how much water is going to flow through the pipe. So again, same type of thing dealing with electrical energy. Okay, now resistivity of various materials. Okay, if material is a good conductor, it's got a low resistivity. Okay, low resistivity. Look at them; they're all about 10 to the minus 8, anywhere from 1.5 to 100, 10 to the minus 8. Okay, semiconductors, materials that are semiconductors, they're in the middle. They're about 10 to the minus fifth. Okay, and insulators, note insulators, they're not good conductors of electricity, so they're going to have a high resistivity. Rubber, wood, okay, resistivity of the materials, rho. Okay, here's an example. Instructions on electric lawnmowers suggest that 20 gauge extension cord be used for distances up to 35 meters, but a thicker 16 gauge cord should be used for longer distances. Cross-sectional area of the 20 gauge wire is 5.2 times 10 to the minus 7 square meters, while a 16 gauge wire is 13 times 10 to the minus 7 square meters. Determine the resistance of the 35 meter 20 gauge copper wire and the 75 meter 16 gauge copper wire. Okay, just a note here, you got 35 meters, 75 meters. When you go to Lowe's or Home Depot and you buy an extension cord, they're not measuring in meters. Again, they're measuring in feet. So 35 meters, again, is roughly 3.281 feet is equal 1 meter. 35 meters is approximately 115-foot extension cord. 75 meters is a 250-foot extension cord. You need an extension cord that long if you got an electric lawnmower. Okay, so we want to determine the resistance of 35 meters of 20 gauge copper wire. So resistance is equal to the resistivity of the material, copper wire, resistivity copper wire, 1.72 times 10 to the minus 8, okay, times the length of the copper wire, 35 meters, divided by the area. 5.2 is 10 to the minus 7. Okay, that's 1.2 ohms. You note I made up a little chart here where I've got the wire, the area of the wire, the safe distance you can use the wire, and the resistivity. Okay, so 20 gauge thick extension cord, less than or equal to 35 meters, 1.2 ohms. Okay, now 16 gauge copper wire. Notice 16 gauge copper wire is a thicker wire. Its area is 13 times 10 to the minus 7 versus 5.2. Okay, so the resistance of the 16 gauge copper wire for 75 meters worth is 0.99 ohms. Okay, again, note what you're after here is you want to minimize your resistance. You want to minimize your resistance. You don't minimize your resistance. Okay, the wire is going to get hotter. You're going to heat the wire. When you heat the wire, the possibility of a fire. Okay, so you want to minimize the resistance so the wire doesn't get hot. Okay, so again, note we calculated 0.99 ohms for 75 meters of 16 gauge copper wire. If we do the same calculation for 35 meters, we get a 0.46 ohms. So again, you want to minimize your resistance. Okay. Now, impedance plasmography. Okay, this is what you use to check for blood clots, basically. Okay, check for blood clots. Impedance is another word for resistance. Okay, so resistance is equal to the resistivity of the material divided by the length, divided by the area. Okay, area is basically the volume of the calf divided by the length. So if you do the math, then the resistance plasmography for measuring distance between two wire electrodes here is the length, the distance between these two electrodes times the volume of the calf. Okay, note resistivity is indirectly related, inversely proportional to the volume of the calf. Okay, so again, inverse relationship here. All right. Okay, if you look back at the resistivities of various materials, you note at the bottom, and you note also, I've got it right here, where resistivity of the material is subject to temperature. Subject to temperature. Okay. If you look on this chart, the list of resistivity of various materials, these values pertain to temperatures near 20 degrees centigrade. Okay. If the material is not at 20 degrees centigrade, you got to make adjustments. Okay. You adjust for the resistivity of the material. Okay, where rho is resistivity of the material. Rho sub 0 is the initial resistivity of the material. Theta, or I'm sorry, phi is temperature of the coefficient of resistivity. Basically, P and P sub 0 are the resistivity at temperatures T and T sub 0. So you got to make an adjustment for the resistivity of the material, and then once you get an adjustment for the resistivity of the material, okay, you also make an adjustment for the resistivity. Okay, here you've got an electric oven, burners on an electric oven. Okay, where you got coils, wire. Okay, the wire becomes hot. You got a casing, you got a metal casing, and you got the heating wire. Okay, the metal casing surrounds the heating wire. Okay, the wire becomes hot in response to the flowing charge and heats the casing. Okay, so that's what puts it, and the length of the wire is 1.1 meters. Okay, so that's how, if you're dealing with heating up something on a stove, then you got to adjust for the resistivity based upon the temperature. Okay. Okay. Resistance and resistivity. Okay. Next topic we'll talk about here is electric power. Okay. And again, okay, power, if you look at my lecture aids, power is equal to the change in energy divided by the change in time. Okay. What do you have? They have electrical energy here. So you have the change in electric potential energy. Okay. You go back to chapter 19, and we talked about the voltage. The voltage, or the electric potential difference, okay, is equal to the change in electric potential energy divided by the charge. So basically what you do is you substitute. Electric potential energy is equal to the charge times the voltage here. Okay? So now you've got the charge over the time. Okay? Charge over time, what's that equal to? Current, I. Okay? So what you've got basically is the electric power is equal to the current times the voltage. Current times the voltage. Very simple. Okay? Current times the voltage right there. Units of power are watts. Other variations, okay, are P is equal to I squared divided by R. And how do you get that? Get that from Ohm's law, where voltage is equal to current times resistance. You just substitute. Okay? You also got power is equal to V squared, voltage squared divided by radius. How do you get that? Again, from Ohm's law, where the current is equal to V divided by R. So you got three variations here of the electric power formula, just like we talked about capacitance. Okay? And I've got them listed right here. Okay, here I've talked about the resistivity of the material adjustments. There's electric power. There's the three forms. Power is equal to current times voltage. Power is equal to current squared times resistance. Power is equal to voltage squared divided by resistance. Three different forms. Okay, here's an example again, a power example. Okay, we're back to the flashlight again. Okay, the flashlight, the current in the flashlight is 0.4 amps, and the voltage, two 1.5 volt batteries, 3 volts. Find the power delivered to the bulb and the energy dissipated in the bulb in 5.5 minutes of operation. Okay, power delivered to the bulb. You know the current, you know the voltage. Very simple. I times V, 1.2 watts of power delivered to the bulb. Okay, energy dissipated in 5.5 minutes. Energy is equal to the power times the time, again from our basic equation. Okay, so you got 1.2 watts, 5.5 minutes is 330 seconds. So the energy dissipated to the bulb in 5.5 minutes of operation is 400 joules, 4 times 10 to the second. Okay, just some other examples here. If you got a light bulb, a 20-watt light bulb. Okay, and I've got this on the lecture aids again. You figure out the current in a 20-watt light bulb. Again, I is equal to the power divided by the voltage. Okay, so the power is 20 watts divided by the voltage of 3 volts. Okay, that's equal to, if the voltage stayed the same, you get 6.7 amps of power. You got a 50-watt light bulb, you got 16.7 amps of power. That's assuming the voltage is constant at 3 volts. Okay, just look at the differences there. Note the electric circuit drawing. You got the source voltage. You got a switch here on and off, and you got the flashlight filament, which is the resistance. Okay. Okay, so that's basically electric power. Okay. You're going to talk a little bit about this before again, but what you basically have is a lot of electrical devices you have around the house. They're really just plain and simple resistors. Okay, toasters, irons, space heaters, etc. Okay, we talked about 2 types of current. We talked about alternating current, and we talked about direct current. Okay, the current coming into a household is alternating current. It's the most common type. Okay, alternating current. Remember what that is? Okay, is the flow reverses direction periodically. It goes back and forth. Okay, so AC circuits are basically circuits with resistor. They're, like I said, electrical outlets in the house. Okay, here you got just a plain toaster application. Okay, where if you look at the electric circuit diagram, the toaster is actually the device that's a resistor. Okay, and you got the AC generator. AC generator is back at the electric power company, back at the plant, and all you're doing, the heating element is a thin wire resistance in that toaster coming through the electrical outlet. Okay, symbol for alternating current is a little circle with a squiggly line in between. Okay, that's the symbol for alternating current. Alternating current, like I said, it reverses its flow periodically. Okay, so it's basically like the sine function. Okay, where positive to negative, positive voltage to negative voltage. You can see the current. It's reversing positive to negative, negative to positive. It's reversing directions periodically. Alternating current. Okay, alternating current. Okay, define the voltage in an alternating current circuit. Let's just take a look at this. Alternating current. The voltage in an alternating current is equal to the V sub 0, which is the max voltage. In the US of A, the max voltage you can have in any outlet is 170 volts, times the sine of 2 pi times the oscillating frequency of the voltage, which is in cycles per second. In the US, it's 60 hertz, okay, times the time, okay? And again, note the 2 pi ft is the angle expressed in radians again, okay? So to find the voltage in an alternating current, there's what you do. Max voltage, times the frequency times the time. Okay? Find the voltage. Okay? In circuits that the current reverses direction, just like I said. Now, if you want to find the current, Ohm's law, Ohm's statement, V is equal to IR, I is equal to V over R. Okay, you substitute. V is now V sub 0 sine of 2 pi f over T over R. V sub 0 over R is basically the initial current. It's the max current. It's the peak current. The peak current. So I sub 0 is the peak current. You just get it from substitution of Ohm's law. Okay, now when you're talking about alternating current, it's a sinusoidal motion. It's average current. Remember, I said that. How do you display average current? It's displayed as called root mean square. RMS is basically the average current, average voltage. You can get power. Okay, power is equal to current times the voltage, right? Back over here. Power is equal to current times the voltage. So we substitute for current, substitute for voltage, and we get our equation for power in alternating current. Okay, very simple. Okay, keep in mind average power because it's reversing direction back and forth. So note the little line over the power is equal to the max current, max voltage divided by 2, which is basically I times I, the average current and the average voltage. I over the square root of 2, V sub 0 to the square root of 2. Here you've got the alternating currents equations, where the average voltage, noted as VRMS, is equal to the average current, noted as IRMS, times the resistance. Power average is average V times average I. Or three different ways to express power there. Okay? Alternating current, power. Here's an example. Here's an example. Okay, you get power sent to a loudspeaker. Stereo system here. Stereo receiver applies a peak voltage of 34 volts. So you know in this example, example 6, okay, that the V sub 0 is 34 volts, max, okay? Speaker behaves approximately if it had resistance of 8 ohms. Determine the average voltage, the average current, and the average power for this circuit. Note the electric circuit diagram has the symbol for alternating current. Max voltage in the alternating current is 34 volts. Resistance is 8 ohms. You calculate the average voltage. VRMS is the max voltage divided by the square root of 2. 34 divided by 1.414 is 24 volts. You calculate the average current. Average power divided by the resistance, 3 amps. You calculate the average power. 3 average current times average volts, 72 watts. Pretty straightforward, alternating current. Okay? Here's another alternating current example that we talked about here. You got these outlets in the house. Okay, during the winter, people use space heaters, electric space heaters to keep warm. However, the heater must be located far from 120 foot, far away from 120 volt wall receptacle, so an extension cord must be used. Manufacturers warn against using extension cords for space heaters because they're a fire hazard. So if one must be used, they recommend a certain wire gauge or smaller. Why? Why are smaller gauge wires better than larger gauge wires? Okay? So resistivity is equal to the resistivity material length divided by the area. Okay? Go back to the extension cord example where we said a smaller gauge wire is a thicker wire, less resistance, right? So it's not going to heat up. Okay, so again, that's slide 14. We talked about the lawnmower cord. So why are smaller gauge wires better than larger gauge wires? Very, very simple. Less resistance. The core is not going to heat up. Tons and tons of house fires are caused by extension cords overheating. So please use what the manufacturer represents for a wire gauge in the extension cord. Okay, we talked about a couple different topics here. Let's do a couple problems here from each one. Okay, let's take a look at resistivity and resistance. Let's look at number 14. 14 at the end of the chapter. Okay, and again, I'll send you the solutions again. 14 at the end of the chapter. Okay, I got a large spool of wire in an electrician's workshop, 75 meters of insulation-coated wire around it. When the electrician connects a battery to the ends of the spooled wire, resulting current is 2.4 amps. A couple weeks later, after cutting off various lengths of wire for use in repairs, the electrician finds that the spooled wire carries a 3.1 amp current now when the same battery is connected to it. So when it was 75 meters long, it had a resulting current of 2.4 amps. When you use some of this insulated wire, okay, you check it again, now it's got 3.1 amps, the same battery is hooked up to it. What's the length of wire remaining in the spool? Okay, so you define what you got here. Initial length, L sub 0 is 75 meters. Okay, the initial current is 2.4 amps. The new current is 3.1 amps. Okay, if you take and look at the equation, resistance is equal to resistivity in the material times the length divided by the A. Okay, you're using the same battery, you got the same wire. Okay, resistance according to Ohm's law is equal to voltage divided by current. Okay, so voltage divided by current on the left hand side, PLA on the right hand side. Voltage is the same because you're usually checking it with the same battery. Resistivity is the same because you get the same wire, and the area of the wire is the same. So basically what you have, you cross everything out, is you got that's equal to the length divided by the current. So it's an inverse relationship. Okay? If the current goes up from 2.4 to 3.1, the length of the wires got to go down. Okay? So if the current goes up 2.4 divided by 3.1, I do my calculation. 2.4 divided by 3.1. I get 77.4%. So the length of the wire is going to be reduced by 77.4%. So 75 meters times 77.4%. Now the length of my wire is 58 meters. Pretty straightforward. Okay? Okay, let's look at another problem. Let's take a look at number 24. Take a look at 24. Okay? 24 says, I got a blow dryer and I got a vacuum cleaner. Okay, blow dryer and a vacuum cleaner each operate with a voltage of 120 volts. The current rating of the blow dryer is 11 amps, and the vacuum cleaner is 4 amps. Determine the power consumed by the blow dryer, the vacuum cleaner. Determine the ratio of the energy used by the blow dryer in 15 minutes to the energy used by the vacuum cleaner in a half hour. Okay? So first of all, I want to determine the power. So power is equal to, I know my voltage and I know 120 volts, and I know my amperage, 11 amps and 4 amps. So I'm going to use my power equation. P is equal to IV. P is equal to IV. Okay, so I'm going to calculate the power of the blow dryer, 120 times 11. I get 1,320 watts. The power used by the vacuum cleaner, 120 times 4, is 480 watts. Okay? That's part A. It's part B. Part C, determine the ratio of the energy used by the blow dryer in 15 minutes to the energy used by the vacuum cleaner in a half hour. Okay, so the energy is equal to what? Power divided by the time. So the energy of the blow dryer would be 1,300 watts of power. Okay, energy times energy is equal to power is equal to energy divided by time. So energy is equal to power times time. So energy of the blow dryer is 1,300 watts, 1,320 that we just calculated, times 15 minutes. Okay, that's the numerator. The denominator would be the energy of the vacuum cleaner, which would be 480 watts times 30 minutes. So that gives you 9,500. That gives you 500 or 9,500 joules in the numerator, 4,400 joules in the denominator. Basically, the ratio of the two is 1.4. So interpret your results here. The blow dryer is using 1.4 times more energy in 15 minutes than the vacuum cleaner. Why is that? Why is that? Right here. Because it has more current. It's using more current. 11 amps versus 4 amps. That's the difference. Blow dryers use a lot more. Okay. Okay. Let's do another example. How about number 33? 33. Alternating current. Okay, 33. Alternating current. The average current in a copy machine is 6.5 amps. And the resistance of the machine is about 18.6 ohms. What's the average power? And what's the peak power delivered to the machine? Okay, average power in alternating current is basically the average amps. Go back and average power would be equal to the average current squared times the resistance, because we know what the current is, we know what the resistance is here. Okay, so basically 6.5 amps squared times 18.6 ohms gives us the average power of the copy machine is 786 watts. Okay, what's the peak power? Okay, well, the peak is twice the average, isn't it? Isn't the peak twice the average? The peak is twice the average. Average is equal to that. Okay, the peak is twice the average, isn't it? Okay, so basically what you have is 2P. So the peak power is going to be 1,572 watts. Again, pretty straightforward. All right. I'm going on here a little bit. Let's do one more. Let's do one more. Let's do one more. Let's do 38. 38. Okay. I got a hot water heater. Recovery time for a hot water heater is the time required to heat all the water in the unit to the desired temperature. Okay. So suppose we have a 52-gallon hot water heater. 1 gallon is equal to 3.79 times 10 to the minus third cubic meters. Excuse me, that again is on the front cover, that conversion. Okay, so 52 gallons, suppose that a 52-gallon hot water heater starts with cold water at 11 degrees centigrade and delivers hot water at 53 degrees centigrade. The unit is electric and utilizes a resistance heater, 124 volts, 120 volts alternating current, 3 amps of resistance to heat the water. Assuming no heat is lost in the environment, determine the recovery time in hours of the unit. What do I got here? Determine the recovery time in hours. Okay? So I've got energy. What do I have here? Energy used to heat the water, right? From 11 degrees to 53 degrees. So I've got power is equal to energy divided by time. I'm looking for the time here, aren't I? Okay, so basically time is equal to the energy divided by the power. Okay? Energy first. Energy is what? MC delta T. Okay? Mass times the specific gravity of water times the temperature difference, delta T. Okay? So Cm delta T, specific heat is 4186 joules per kilogram degrees centigrade. Mass of the water. I don't know what the mass of the water is, do I? Okay, but I know density of water is equal to mass divided by volume. I've got the volume here. Okay, so I can so the mass of the water is equal to density 1,000 kilograms per cubic meter. Okay, times my volume, 52-gallon tank times 3.79 10 to minus third cubic meters. Okay, I can calculate my mass. Okay, and I should come out with approximately 200 grams of water. 197 grams, you call it 200. Okay, and I've got my temperature, delta T. I'm gaining temperature, so it's 53 minus 11, 42 degrees. So I calculate my heat energy that I need to raise that water temperature to 53 degrees and recover is 3.46 times 10 to the 7th joules. Okay? That's my numerator. My denominator is power. I know my voltage, I know my resistance. Okay? So I can look at my equations and I can use average power is equal to the average voltage divided by the squared divided by the resistance. Okay? So that's going to be 120 squared divided by 3 ohms. If I calculate the average power there, I've got 4.8 times 10 to the third watts, 4,800 watts. Okay? The time for that hot water heater recover then, numerator is 3.46 times 10 to the minus 7th joules divided by the power, which is 4.8 times 10 to the third watts. I come up with about 7,210 seconds. 0.721 times 10 to the fourth. 7,210 seconds. What is that? 3,600 seconds in an hour. It's about 2 hours. It takes 2 hours of time for that hot water heater to recover if it's fully drained. If you drain the hot water heater the whole way and deliver hot water, 11 degrees, 53 degrees. Now you can do calculations on this if you can calculate how much water you drained out of the hot water heater, for how much water to take a shower, etc., etc. Okay, good problem, good equation. Okay, that's pretty much it. Example wise, I gave you a couple examples. This is basically the lecture for Thursday. I'll see you all in about a week and a half. Take care. Thank you.